All right, thanks a lot, Alicia. Thank you for inviting me. It's a great pleasure to present here. It's lovely to see that there's a place where you're really focusing on interdisciplinary research. I think particularly on AI nowadays, things are becoming more and more interconnected. So it's really important that we find a common language between different fields. It's the only way to really advance in here. And I would really like to talk more a bit afterwards about this project on delegating punishment, because it's also something I have a project going on with Portugal, with Francisco Santos, about delegating rules. But anyway, we'll talk more about that later. So the questions, as Ali said, the questions that I've been looking or interested in during my PhD, and I'm still interested in, is the question of cooperation in human societies. And particularly in cooperation in some specific situations where there is some kind of conflict. And this conflict may be between private and public interests. It may be moral, like in the question of the moral machine, that the paper of Elias, like you see here, you have an autonomous car that at some point may not have a decision. It will have an accident, and it has to decide on either to kill some people or kill the other, and it has to take into account the interests of the owner as well. But the conflict, and this is the what I've been most interested in, the other conflict that may arise is a temporal conflict. And when I say temporal, I mean a conflict between immediate outcomes and future outcomes, immediate rewards and future rewards. And the reason why this is important is that we know that in certain situations, humans are not very good at looking ahead, at actually making long-term plans, evaluating long-term consequences of their actions. And there are many problems in society that have these characteristics. And a big example is climate change, climate action, where you have many different countries with different political views, different economic situations, and they all have to cooperate to avoid a future climate catastrophe. But some of these countries, let's say developing economies, for example, the initial measures that need to be taken may have a negative impact in their industry. So they may say, okay, I'm not going to do anything now, and I'm going to hope that the effort other countries put is going to be enough. But if the situation persists over time, that we end up in the result I said before, we have a climate catastrophe. And so we really need to plan ahead in this kind of situations, because there is a collective risk that we are all going to be affected. And climate change is not the only example. You also had group hunting in prehistory, where humans had to coordinate to hunt bigger prey instead of just going for small rabbits. But if they don't coordinate, and there's some risks involving this activity. There's also vaccination hesitancy, for example. Now in the COVID, if we don't take the vaccine, the situation will just go on, and antibiotic abuse. Now, all these issues nowadays are not only influenced by our discussions between humans, because a lot of the information that we are getting is coming from social networks or YouTube videos, for example. And this information has been filtered and often recommended by us by AI systems. And this has an impact on our behavior. But also, we are delegating more and more of our actions to these AI systems. For example, I no longer choose a route to go anywhere. I just ask Google Maps. Or an extreme example is the figure you see here in this slide, this smart refrigerator, which not only sees what is inside, but can also find out what we normally like to buy and make an order on our behalf. And this definitely has an impact on consumer behavior. The question is, what is this impact? And this is what I'm going to talk about with the experiments I'll present to you today in this talk. We are going to try to find out whether this impact in my context is positive or negative, and in which cases it might be positive or negative. Of course, all these examples that I have presented are very complex. and I'm not going to be able to model them completely. So what I'm going to do is I'm going to abstract them into a game theoretical framework, which allow us to study the particular features we are interested in. So just to make the talk a little bit more organized, I want to say that I'll first introduce the collective risk dilemma, which is the theoretical framework we'll use, and afterwards I'll present our experimental setup. I'll first focus on the experiments done with humans and the results, and afterwards I'll look how this outcome changes when we delegate to artificial agents or we interact with them in a hybrid setting. Okay, so just to start, let me present the collective risk dilemma. The collective risk dilemma has a very fancy name, but it's a type of public good game, in fact, a threshold public good game, in which we have a group of players that start with an equal endowment. In this case, if I'm not mistaken, it's 24. And then they are asked to make stepwise discrete contributions throughout different rounds to a public good. And these contributions may be either 0, 2, or 4 at each round. So what you see here is that you have the first player that contributed 2, the second player didn't contribute anything, the third player contributed 4, and the fourth player didn't contribute anything in this round. And so these players make contributions throughout different rounds, and at the end of the game, if they surpass a particular threshold or collective target, which in this case is 48, then they all may keep as much of their endowment as they didn't contribute. This means that even if you are successful, if you reach the collective goal, you may end up in an unfair situation. So some people end up with more payoff than others. However, if the collective target is not achieved, then there is a risk that everyone is going to lose the rest of their endowment. And so this risk parameter simply defines the probability that this event may occur. And so in this game, you have this trade-off. From one side, you would like to contribute as little as possible to maximize how much you may get at the end, but you need to balance that with the probability that you may actually lose all your remaining endowment. And now I'm going to show you some previous results in the literature. One of the first experiments, I think the first experiment performed in this dilemma, was done by Milinski, and what he showed, which I think was the director of a Max Planck Institute in Brunn, if I'm not mistaken, but anyway. What he showed is that only when the risk, the probability of the disastrous event happening is very high, groups actually start to be successful. So people will start to cooperate. But even in this case, you see that in his experiment, only 50% of the groups managed to be successful, even though participants would lose their endowment with 90% of probability. If you look at theory, theory says that in this case, players should contribute almost all their endowment to reach the target because the utility is very low if you consider the disastrous event. But you see that humans don't really do that. So they are not coordinating well. And we're going to try to see why. This was also shown through theoretical models. What you're seeing here is the result of a simplified evolutionary model where they consider a population of agents and they look at which states this population may end. So in the x-axis, you see the possible states, so either 0 cooperators or 100% of cooperators, and in the y-axis, the probability of this state happening. And what it shows that only when the risk is very high, you're spending the system is spending most of the time in cooperative states, and when the risk is below 50%, most of the time the system spends in defective states. I'll talk more about these types of models later in the talk. We also had our own theoretical model using population of agents, which adapt using reinforcement learning. And what we see is that in this type of game, we actually identified 3 different zones. First, we have a defection dominant zone where the risk of the game is smaller than the cost, and the cost in our case is basically half of the endowment. So it means that to reach the target, players need to contribute. If every player contributes half of their endowment, then they will reach the target exactly. That's what it means. Then you enter in some transient zone where cooperation starts to increase, and finally you are in a coordination zone where players actually have to coordinate to manage to achieve the target. And just to show again the experimental results of Milinski, that's what you saw. And what we repeated these experimental results. We repeated this experiment with humans. We obtained a slightly higher collective success, but actually just before the pandemic started and stopped all our experiments, we had performed another session and we saw that this was going down. I didn't aggregate these new results because I don't know what is the effect of having the pandemic. But then in any case, it's just clear that even under high risk, people are not that good at coordinating. Now there is another experiment, so this blue one, in which they included communication. So they allowed participants to pledge, to tell others how much they wanted to contribute during the game before the game started. And then they achieved 100% of cooperation. So it's clear that by having a communication mechanism, you solve the coordination problem. However, it's not that simple to design a communication mechanism. And in the same experiment that they showed us, they also had a treatment in which they added uncertainty about what is the goal you need to achieve. What is this collective target that has to be achieved? And then suddenly communication started to be used strategically. People didn't said one thing and then did another, and cooperation and group success went down almost to zero. So even though communication may solve the coordination problem, we also need to find other mechanisms. And this is one of the reasons why we started to look at using delegation to artificial agents or interacting with them to try to overcome this issue. So now let me introduce you our experiment. So in the photo, you see the place where we did the experiment. It's basically a room where we put a number of tablets and people are separated with this screen so that they cannot see each other nor communicate. And we get real people. Now we're trying to do experiments online as well. So we had 246 participants. Each participant started with an endowment of 40 units, and they had to reach a target of 120 units. Each group had 6 players. This means that if every participant contributes exactly half of their endowment, so 20 units, the group reached the target exactly. We only considered the high risk case, so only 90% risk, and the experiment had 10 rounds. So we had a human treatment where humans play this game. We had 72 participants in this treatment and 12 groups. And then, in the first part of the talk, I'm going to focus only on this treatment, but we also had a delegate treatment with 90 participants in which we asked participants to select an agent out of a pool of agents. And this agent is going to play the game in their place. Then we had a customized treatment in which participants could design their agent, could select some parameters that will define the behavior of the agent. And finally, we had a nudge treatment. I'll explain later why we call it nudge, but it's simply a hybrid experiment in which in each group there's half of the participants are humans and half of them are artificial agents. And we had 48 participants. In these 2 last treatments, our experiments were stopped due to the pandemic. So we still have to do more experiments, more experimental sessions, but we already can observe some very interesting trends, which I'm going to show to you.
Elias, sorry to interrupt, and
Yes.
I hope I'm not really the only one. But
Please.
when they select an agent from what options do they have? Like, what's the difference between different agents?
I'll explain that a little bit later, but they basically have 5 options. These options have been selected based on the behavior of human players in the human treatment. I'm going to explain that in a little bit. And participants can see the full behavior of the agent before selecting.
Okay.
So they have full information in this experiment about how the agent will behave. I will go in a bit more detail in a moment. First, let me show the human experiment. Thanks for the question, by the way. So this is also doing the human experiment and also in the hybrid experiment treatment. This is what people could observe. They could observe how much they contributed in the previous round and how much the other members of the group contributed in the previous round. And this information is always shown in the same order so that participants can form some kind of history about the players, although they don't know in the room who is in the room. And groups are assigned randomly. They could also observe how much is in their personal account. And they were given pen and paper to keep track of how much they were contributing and how much is in the public pot. During this first experiment, and in the hybrid experiment, we also asked participants to make predictions about what the other members of the group are going to do. And this is kind of an error check as well, allows us to see if people were keeping track of what was happening in the experiment. Sorry. So as I said, in this experiment, the human experiment, we had about 67% of success, which is not very high, considering that the theoretical model tells us that it should be 100%. And here, what I'm showing to you is in the x-axis, the number of rounds, and the y-axis, the average contribution of players per round. This is an aggregation of all the players in the human treatment. And what we see is that the main difference between successful and unsuccessful groups appears to be in the last rounds. While successful groups increase their contributions, unsuccessful ones decrease their contributions. So it appears indeed to be a coordination problem, but let's look a little bit more to try to understand exactly what is going on. So now we have a much more complicated figure, but simply what I'm showing is now the frequency with which each action is played at each round. Again, this is an aggregated measure. What we see here is that the initial action that most participants play is 2. And again, if every player plays 2 in every round, they will the group will reach the target exactly. So the initial intention of participants is to cooperate, but something happens during the game. You see that in both successful and unsuccessful group, the trend of playing 2 is decreasing. The difference is that in the unsuccessful groups, we have an increase, the rate of decrease is much bigger of the action 2, and we have a big increase of people defecting, of playing 0 in the last rounds. But clearly, there seems to be some coordination issues here that we need. And the question, and one of the hypotheses that we had, or at least one of the motivations we had with the work I'm presenting today, is how can we make people keep this initial intention throughout the game and not fall into the temptation of deviating towards a different plan. So another thing we did is we clustered the behaviors of all participants in this experiment using the DB scan algorithm. I can talk more about it later, but what is important is that we find mainly 5 clusters and then some outliers, which are this blue bar, which is the blue bar. If we look first at the smaller bar here, the purple, and we plot the average contribution of a player in this cluster with respect to the contributions of the other members of the group in the previous round. So we are trying to plot conditional behavior here. How are the players reacting to the rest of the group? What we see is that these players seem to act reciprocally. They contribute more if the other members of the group are contributing more, and they contribute less if the other members of the group are contributing less. Now let's look at these other 2 clusters, the green cluster, which is the biggest cluster in this treatment, and the orange cluster. What we see here, if we look at the green cluster, it seems similar to the purple cluster, so you would assume that it's, again, a reciprocal behavior, but in fact, most of the time in the game, players will be, the other members of the group will be contributed around 6 and 16. So in fact, this player is behaving mostly fairly. These players are mostly given always 2 during the game. Now, this orange cluster seems to give a little bit more when the other members of the group are contributing less. So it's slightly compensatory. But again, take into account that some of these points have a big variance, okay? So there's different results, and some players are more compensatory than others. We are not looking at individual behavior here. Finally, if we look at this red cluster, what it appears is that it's again very similar to the green. It seems that it's players cooperating most of the time, but it appears there are players that are giving a little bit more than in this green cluster. They are being more altruistic. And finally, if we look at what's going on with the outliers, we see that, and again, there's a big variance in some points, but we see that there are some players that are giving very little. They're mostly defecting. So we cannot, if we look at these 5 behaviors, we can enumerate them. We can say that we have three unconditional behaviors. So people, of course, this is again an abstraction, it's a simplification, so that we can model this. Since we don't have big data, we have 246 participants, not 5,000. We have three unconditional behaviors, so people that are contributing always 0, those that contribute always 2, and those that contribute always 4. And then we have two conditional behaviors, those that are compensating, so giving more when the rest of the group is giving less, and vice versa. And those that are reciprocating, only giving if the rest of the group is also contributing. And now we can plug these 5 behaviors into a multi-agent model of social learning. And the way this model works is we consider...
It's a question by Tamir, maybe just please interrupt.
Please.
Yeah. I was just wondering about the previous plots in the slide before.
Yeah.
Yeah. Okay, I just want to make sure that the x-axis here is the previous contribution, not related to the number of rounds. So this is not sequential data about how things were progressing.
You're correct. This is not sequential data. It would be very interesting to do that, but we don't have enough data to aggregate over each round. We need to do more experiments for that. So this is aggregated over all the rounds. So you're correct.
Yeah, thank you.
You're welcome. So the way this evolutionary model works is that we consider a population of strategies. Here you see 4 strategies. And we apply some evolutionary pressure over these strategies. So there's some selective pressure in a way that strategies that are performed the best are going to be imitated more often by other strategies, and in the long run, they are going to invade the population. They're going to dominate the population. Also, in this process, there is some mutation. There is some randomicity. Stochasticity. So in some occasions, with a very low probability, some strategies mutate into a different strategy. And if we had 3 strategies, we could actually plot this dynamics into a simplex, such as in this figure. And if, for example, dynamics were following what you see in this figure, you would see some kind of chaotic dynamics, like in rock, paper, scissors, where no strategy is dominating. You end up one strategy invading the other, and so on. However, this type of models, as the number of strategies increase, become quite computationally hard. So an alternative is to consider a simplification, which is when mutation is very small, it is enough that we look only at the edges of the simplex. And looking at the edges of the simplex, it means that we simply need to consider what is the invasion probability of each strategy over the other. So to be a bit more clear, let me go a bit more in depth in how this Moran process works. So you start with a population of strategies at a particular time step at a generation. Here you have 2 strategies, and you select one strategy at the particular generation, and there is a probability that this strategy is going to mutate and be replaced by another strategy in the population. Otherwise, with probability 1 minus mu, you are going to select another member of the population, again randomly, and you'll compare the fitness of these 2 members. The fitness is defined by the utility of these strategies. And following this Fermi function, the difference in fitness is transformed into a probability value that defines how likely a strategy is going to imitate another one that is performed better. And this process is performed over time, and this beta value simply defines the intensity of selection, which is how much the difference in payoff matters for the evolutionary dynamics. And if you assume, again, that mutations are very rare, then you can actually look only at the edges, which is defined by this Markov chain, and look at what happens if you introduce one mutant in a population of another, in a monomorphic population of another strategy, and what is the likelihood that this mutant is going to invade the population. And if you consider this simplification, then you can plot this Markov chain with the 5 strategies that we said before. We consider a very small selection strength, so we are looking at a small selection. I will show in the next block why we go for this value. And what we see in this Markov chain is that the always 0 strategy is dominant. It is not invaded, so the arrows here mean a strategy being invaded by another strategy. An arrow in that direction means that reciprocal is invaded by always 2. And so always 2 is never invaded by any other strategy. And following this stationary distribution, the stationary distribution values are on the top to find the probability that you're going to be in any of these states. You can calculate what is the expected fraction of successful groups, which is 52, if I remember correctly, which is very close to our experimental result. And the reason we choose this beta equal 0.04 is simply to fit the results to our experiment. We can actually look at different values of selection strength, and as selection strength increases, then always 2 becomes more and more dominant in this particular scenario. So just to summarize, I want to say that humans, with this first part, I want to say that humans are not that good at coordinating under high risk without any form of communication. And that from the experiments, we can extract mostly these 5 strategies, always 0, or always 2, always 4, compensator, and reciprocal. And that we can use this very simple model to reproduce the main trends of the dynamics we observe in the experiment. So now let's go back to our experimental setup and let me talk a bit more about these other 3 treatments that I left a little bit behind. So as I said before, following the question of your colleague, in the delegate treatment, participants have to select an agent out of a pool of agents. In the customized treatment, they will actually program the agent, select some parameters that will define the behavior of the agent, and in the nudge treatment, they will interact in a hybrid group. And the questions we are looking here at is how delegation and hybrid interactions affect the outcome we saw with only humans in this game. And I'm showing here some papers that can be relevant. What we see in the literature in the case of delegation is that when humans, for example, when they are able to customize the agent, when humans design the agent, they tend to do this closer to game theoretical concepts. And sometimes this can be bad. The agents might be more selfish. From another point of view, since humans are not playing in the game, the role of emotions is different. And that might be the feeling of, there's this effect, you see here, betrayal aversion, that is known in economic theory, that is, I don't cooperate because I'm afraid that you will not reciprocate. It's some kind of action before the fact actually occurs. Another thing that is important to take into account is that particular theoretical solutions don't work when you have humans because they have emotions. An example is that during the human experiment, after each experiment, we have a small questionnaire with different questions, and one of them is simply for them to tell what was their experience during the experiment. And there were, in some groups, you had some players playing a Nash equilibrium solution, which is in the first half of the game, you don't contribute anything to the public good, and in the second half of the game, you always play 4. So you contribute everything only in the second half of the game. It's called a wait and see strategy, and it's a Nash equilibrium of the game if everybody plays that same strategy. The problem is that the other participants of those groups afterwards wrote in the comments, said that they decided to stop cooperating. So they were cooperating in the first half, and then they suddenly stopped, even though these other members started to contribute 4 all the time. And they simply said, no, I was mad at this person. I didn't want him to get anything. I would prefer that we all lose instead of this person getting something. So when dealing with humans, we have to take into account that not all theoretical solutions are valid. In the case of hybrid interactions, it's also, there's some experiments that show that humans tend to act more selfishly when interacting with machines, which can be an issue. At the same time, because not everybody in the group is human, maybe there's a diminishment in social punishment, which might be positive in this kind of high-risk situations. So again, going back to the experiment, in the first experiment, in the delegate treatment, we actually simply gave to the participants 5 choices, which were exactly these 5 behaviors that we identified in the human experiment. So always 0, always 2, always 4, reciprocate and compensate. And people could see exactly what was the description of the behavior of the agents before making the action. Of course, we never call the agents reciprocate always 2. The agents are called A, B, C, and D, and they are randomized so that there's no effect regarding this. Afterwards, in the customized treatment, people had to select 5 parameters. It seems quite complex, but you can think of the behavior of the agent in the following way. In the first round of the game, the agent is going to give the action 0, and afterwards, the agent is going to look at what the other members did of the group contributed in total in the previous round and compare it to the personal threshold selected by the participant. If the other members of the group contributed more than the personal threshold, then the agent is going to give action above. Otherwise, if the agent contributed less than the personal threshold, the agent is going to contribute action below, and in another case, it's going to be contribute this action M, action in the middle. And again, you can think of this from the perspective of this reciprocate cooperate effect compensate behaviors in a way that if the action below and above are positive, then the agent is cooperative. If they are 0, the agent is defective. If the agent is giving more above the threshold than below, the agent is reciprocates, and otherwise, if the agent is giving more below the threshold, the agent compensates. And in this experiment, the participants could again see everything what was happening during the game, but they had no agency. They could only see what the agent had selected in this round. They could also follow what was in their private account and what was in the public account. Finally, in the last treatment that we called nudge, we actually took the agents that were programmed by people in the customized experiment. So we did not program these agents ourselves. And we only took the agents from successful groups. And our hypothesis here, somebody's asking a question. No, sorry. So our hypothesis here is that these agents must embed some characteristics that are important for group success in this kind of games. We'll see if that is true. Finally, in each group, there were 3 humans and 3 agents. And also, participants again could see, like in the human experiment, what the other members of the group did in the first round, and we always kept people, human participants and agents in the same order, so that afterwards we could check whether people identified who were agents and who were humans. But we didn't tell this to participants, so participants didn't know who were the agents or not. And then afterwards, I have some results. I can show it to you. People actually cannot discern between humans and agents in this experiment. So let's go to the results. So we had 67% of success in the human group, but when we go to delegate and customize, we see a boost in group success. It goes to 87.5%. So it appears that delegation in this kind of context is good for group success. Finally, in the nudge experiment, we did not see almost any increases. It's very similar to the human results. So it appears that our agents did not manage to nudge cooperation in the humans. So let's try to find out a bit more at what is going on here. So now if we look at the delegation, the results of the delegation treatment, on the left, what you're seeing is again the stationary distribution of our model that we made for human participants that I showed earlier. And on the right, you see the distribution of choices of agents in this experiment. And we see that the always true strategy is very similar to the model that we designed. However, we see a big decrease in the selection of the always 0 in the defective strategy, while there were many more participants selecting always 4 and reciprocation, which are behaviors that are good, are positive for achieving the collective goal. So it appears that in this case, by forcing participants to delegate, they are tending to select strategies that are better for collective success. Let's see if this trend persists in the customized experiment. Of course, this experiment is a bit more complex. There are many more behaviors. So first, in this graph, what you're seeing is the distribution of personal thresholds that was selected by participants. And most participants selected an intermediary threshold, so 12. Threshold could be between 0 and 20. However, you still have some participants selecting very small thresholds or very big thresholds. So what we're going to do in order to be able to classify the agent behaviors is we're going to divide them into 3 groups, into those that selected a very small threshold, those selected an intermediary threshold, and those that selected a very big threshold. And we'll say that for agents with a very small or big threshold can only display unconditional behaviors, so always 0, always 2, or always 4. And only the agents that have an intermediary threshold can actually display conditional behaviors. And the reason for that is simply because in those cases, most of the time, the agent is just going to give one of the actions. So using these 3 groups, we end up with this very complicated plot where you see many, many behaviors, but in fact, a lot of these behaviors can again be classified into compensating. And if we look at this middle bar here, where we are in the intermediate in group, we see that compensation now is the main strategy selected by participants. We also have some reciprocals, which are minority. And if we look at the overall frequency in the population of participants, we have that most 41% or about 42% of participants selected compensatory behaviors. And about 10% of them selected reciprocal behaviors. But again, we see a lot less people selecting behaviors that are very defective, that are contributing almost 0. So this means that once more, participants are selecting behaviors that are good for achieving the collective target. And the explanation that we find behind this is that by forcing them to make this single decision of which agent they have to choose, they need to think about the long consequences of their actions. And we saw in the human experiments that the initial impulse, their initial plan is to cooperate. And we have, and so the delegation here to agents is acting as a commitment device. It's forcing participants to commit to this initial cooperative plan and not to fall in the temptation to deviate to another behavior that will cause coordination issues. Finally, if we look at the results of the hybrid experiment, so here in the graph, you're seeing a very similar one that we saw before for the human experiments. And again, here we are in this hybrid experiment, in this plot, I'm only looking at the results for humans. And what you're seeing is, again, the frequency of each of the possible actions per round, 0, 2, or 4. And what we see is, again, most participants at the beginning prefer to cooperate, to play 2, like in the human experiment. But the difference now is at the end. We no longer see a big difference between unsuccessful and successful groups here. So what is going on? Why we didn't see more cooperation? So let's look now at the average contribution per round. Again, aggregated over all participants, and we separate the contributions of humans and of agents. And in black, you see the human experiment, the one we had before. We call it NU because it had no uncertainty. And what we see is that in the successful groups, the contributions of agents and humans is synchronized from the very beginning of the game. While in the unsuccessful groups, it is actually unsynchronized by 1 tempo. Of course, we still need to perform more experimental sessions in this treatment, but it might be that we need to find a way to better coordinate the behavior of humans and agents from a very early point so that we can increase success in this type of hybrid scenarios. Finally, at the end of each experiment, we had this questionnaire, and in the delegation and customized experiment, we asked participants if they were given the option, would they delegate their actions again to an agent, or they would prefer to play the game themselves. And in both cases, most participants actually said that they would prefer to play the game themselves, even though we know that delegating improves success, and in the end, they may end up going home with more money. But in the customized treatment, we see that more people are willing to delegate. So there might be a relationship between trust in these agents and the ability to personalize, to embed a little bit of your agency, a little bit of your goals into these agents. Finally, in the hybrid experiment, we asked participants whether they thought that humans or agents made more effort during the experiment. And in the failed groups, 80% of participants said that the agents were making less effort, that humans were the ones actually putting all the effort. And this was not true. In fact, agents are making very, very slightly more effort than humans, 33%. But even in the successful groups, almost 50% of participants think that humans are making more effort. And this, again, is not true. The agents in this case are making almost 8.5% more effort than humans during the experiment. So clearly there is a negative bias against the agents, and this might also be influencing the results that we observe. And this is something we need to take into account when designing this kind of systems. Now, finally, I also want to show to you that although we saw an increase in collective success in all the experiments with agents, either in delegation or in hybrid interactions, we see much more variance in the payoff of participants, meaning that you had some participants going back home with a lot more than others. So the situation may be quite unfair in comparison to the only human experiment. And in fact, if we take into account that, again, in this experiment, if participants contribute exactly half of their endowment, they reach the target exactly, and we call this measure the fair contribution, then we can see that in the hybrid experiment, there is an increase in polarization. There's less people contributing exactly this fair amount, and more people contributing less or more. However, we also observe one good effect. In the human experiment, this NU treatment, most contributions were done in the second half of the experiment, which contributes to these coordination issues. But in the hybrid experiment, the agents managed to nudge participants to contribute earlier. They are making more contributions in the first half of the experiment. This is something that, and again, this is higher than in the human experiment. This is something we need to look further into. Okay, so I think I've already bothered you too much with my voice. Let me conclude. So just to summarize, acting through autonomous machines, so delegating seems to increase collective success in our setup. Customization increases trust. When delegating, participants avoid non-cooperative agents. And in the hybrid setting, success might be related to this ability to coordinate from an early point in the experiment. And also that in the hybrid setting, we saw that participants tend to place the burden of failure in the artificial agent. And again, the explanation of why we see an increase of success in the delegation treatment is that these agents are acting as commitment devices. They are forcing people to look ahead, to plan ahead, to anticipate, and look at the consequences of their actions and to stick to their initial plan, which appears to be cooperative. Finally, these are the other people that have done this research with me. A lot of the work was also done by them. And anyway, I'll be very happy to answer your questions, and thank you for your attention. I hope I didn't go over the time too much.
Thank you very much. Really exciting talk. Very interesting. So yeah, happy to receive questions. So whoever has some, please just feel free to talk.
Okay, one question, Elias. When you mentioned the measurement of effort, how did you exactly phrase it? Because I could see some people just perceiving autonomous agents not to exert any effort.
The question exactly was who did contribute more during the game?
Okay.
Okay. So that's the effort. In this case, it's very simple because the game is all about making some objective contributions.
Gotcha.
In other occasions, indeed, it can be a bit more complicated.
And these measures were not incentivized, right?
No. After the experiment, after the experiment in the post-experiment questionnaire, this doesn't influence at all their money. The money they got during the experiment is they already know how much did they receive. So this has, I guess, an impact in their answers because they know how much they received, and this is translated into euros. So I think they could get out between 2.5 euros and 32 euros. Gotcha. So they know this before answering the questionnaire.
So this is a different measure than the beliefs that you mentioned at the very beginning, right?
Exactly.
Okay.
So when you say beliefs, do you refer to
well, you mentioned at the very beginning that you asked people how how much they think others would contribute.
Yes, indeed. This is a different measure. This okay. We did it in the. I'm not showing the results here. Actually, I could have put it on the slides. I normally don't show the results because they are a bit noisy. There are some players that we asked them to predict how much was in the public account, and some players predicted only how much did the other contribute in the previous round. Of course, you can fix that. It's just a bias, but anyway, people are quite good at predicting what was happening. I have some work that I'm doing now. I'm trying to find out. So this is indeed an objective measure. After each round, they had to predict before seeing what the others had done, how much was in the public pots. And in fact, they have some information, and then the information that they actually have to predict is how much the others contributed. And what I'm looking into now is this kind of cognitive bias, in the sense that do people that defected in the previous round expect that the others are also going to defect, or the other way around? And in fact, the results are quite interesting on that, but I still didn't finish the analysis. Just too many things to do. But I think I have it on a notebook. I can open it if you're interested later.
There's another question by Taha.
Yeah, thank you very much, Elias. Fascinating. A lot of interesting results. One of them that surprised me the most was when we reported that people who delegated to the bots, they chose machines who are better than themselves. They are more cooperative than themselves.
Yeah.
And that I don't understand, because if I want to kill someone and I find it difficult and I feel guilty, I hire someone to do it for me. So I wouldn't hire someone who is better than me or more collaborative, right? I'm sure there is a theory behind that, but I was wondering what you think about it.
This is indeed surprising. There are two parts to answering this question. One is that indeed, if you look at the principal agent relationship in economics, so for example, the Hammond paper on strategic delegation, most results found in delegating to humans are indeed negative. People tend to be way more selfish. They use delegation to transfer the burden, and there's a lot of examples in reality. Companies, instead of firing people, when they have to fire a lot of people, they seem to delegate this to another company. So indeed, it's a bit surprising that the agents don't work like that. But there's another part to this answer, and it is that, as I said at the beginning, in this game in particular, in this very high risk scenario, the best thing for everyone is to actually cooperate to reach the target, because otherwise, if you don't reach the target, there's a big chance that you end up with nothing. This doesn't mean that there is no defection. There's still greedy players, and that's what we saw in the human experiments, and we still see this here. There's still greedy players that want to get as much as possible and go into this risk of not reaching the target. But in fact, in this game, the best is for everyone to reach the target. And what is happening here is that, or at least our theory, we cannot prove that yet. At least the experiment, I think we need to design another experiment to completely prove this, is that in this case, the agent is, as we saw in the human experiments, people are actually wanting to reach this. Most people are wanting to reach this good result to actually achieve the target. They want to cooperate. And because you only select the agent once, you're forced to commit to this particular behavior. You cannot, if your initial impulse is to cooperate to reach the target, you cannot change it anymore. And so people probably risk aversion increases a lot in this experiment. When you have delegation, people feel even more afraid than before of not reaching the target. So for me, these are mainly the explanations.
Thank you.
So maybe one last question by Ian.
Thank you for an interesting talk. Just a follow-up question. Did you manipulate? I'm sorry if I missed this part because I was doing a kindergarten pickup in the meantime. Did you manipulate risk? How risky the task was? And is your hypothesis that if you manipulate that, if you have a low risk scenario, then the results might reverse? And just a related question is, do you think that this is this would be the same pattern in like delegation to leadership. Like let's say, you know, in any, like you just delegate to somebody to make decisions on your behalf because, you know, it's a high risk scenario, which is why people kind of, you know, give up more of their freedoms when there's like uncertainty, for example.
Yeah, thank you a lot for the question. So regarding the first part, let me go here. We didn't manipulate risk in the experiment. We only considered the high risk scenarios. In the experiment with humans, there was this experiment from Minsky, and it basically shows that for 50% or less, there's almost no cooperation. Then there were some other experiments done by Tavoni in which he finds very different results, but the experiment is slightly different. So I don't take it into account here. Manipulating the risk is something we are doing now. We're going to start soon with some online experiments with 50% of risk. And indeed, I do expect to see less cooperation. And it would be very surprising if the agents are, I mean, then we will have to find a different explanation here. If delegation still manages to keep success, which would be surprising, then I think it would be a very interesting result. But I do expect indeed that if the risk is smaller, there will be much more noise in the system. Finally, I forgot what was your last question, sorry.
It was about whether this, you think this would also hold in giving up freedom in general.
Yeah, so the delegation to leadership, there is actually also another experiment by Minsky, and I think by Tavoni, in voting delegation. So they had to select some representatives. I don't remember now what was the result, but I'm pretty sure that it increased success in this case. I think it in this kind of problems, it may in fact have a positive outcome, just because by delegating to one person, to a leader, you're actually reducing uncertainty, reducing behavioral uncertainty of the other players, which is a big, which plays a big part here. We know from different experiments that uncertainty doesn't go well with human decision making. In fact, I didn't show it here, but my first experiments were looking at timing uncertainty, what happens if the number of rounds is uncertain. And what we see is that cooperation drops. In different experiments with uncertainty, there were cooperation just disappears. So whatever you can do to reduce behavioral uncertainty and uncertainty in general is good.